Hello, this is the second part of a series of videos about dynamic simulation of power-to-gas processes with the Apros simulator. Here we will delve into the details of water electrolysis modeling. The basic inner structure of the water electrolysis is seen here. This structure corresponds to an alkaline electrolyzer, but we have also developed models for PEM and SOEC electrolyzers. Water is split into hydrogen and oxygen using electricity, and this happens in the cells. These two gases are then taken out from the electrolyzer circulations. In this electrochemical process, heat is released and the electrolyzer is cooled with two circulations, one for the hydrogen side and one for the oxygen side. We will now take a look at how the Apros model is done. The power-to-gas process is shown here in the Apros simulator. On the left, we have the electrolyzers. The model contains three identical alkaline electrolyzer blocks. Each of the electrolyzers takes an input of DC power and based on this calculates the amount of gases produced and heat released. The model is connected also to a cooling water supply with which the cooling is arranged. Next, we will delve into the inner structure of the electrolyzer model. The model contains three main parts: the electrochemical part, extraction of gases H2 and O2 shown here on the right, and the cooling circulations. The electrochemistry is modeled with the so-called IV or current voltage curve, which includes a temperature dependence as well. Based on the voltage and current, the molar flows of the gases are calculated and then extracted. Finally, heat release is calculated. This heat causes the temperature of the electrolyte and the metal of the device to gradually rise. The dynamics of this rise depend on the physical dimensions of the electrolyzer, amount of thermal mass, and the amount of electrolyte, which are the input parameters defined by the user. The heat needs to be transferred out of the electrolyzer, and for this, cooling circulations are modeled. The model used here is the well-known epsilon NTU model for countercurrent heat exchangers. Now we will show a sample simulation with the electrolyzer model. The simulation results are shown on two time series trends. On the top we have the DC power, black line, in megawatts fed into the device, and on the bottom the mass flow of hydrogen produced, blue line, as well as the electrolyzer temperature, red line. Also on the top chart we show the frequency of the electrical grid to which the electrolyzer is connected, green line. In the simulation, the electrolyzer is used in electrical grid frequency support for the first 50 minutes. This means that the electrical power going into the device reacts to the grid frequency. Low frequency, low power, and high frequency, high power. There is a dead band around the nominal frequency of the grid, which is 50 Hz. In the last approximately 40 minutes of the simulation, the electrolyzer does not participate in frequency support, but rather takes a constant power from the grid at two levels, first at 2.8 megawatts and then at 1 megawatt. During this time, the frequency has no effect. Looking at the lower chart, we see that the hydrogen mass flow, the blue line, reacts fast to power input changes. On the other hand, the temperature reacts less aggressively. This is due to the thermal mass, i.e. metal and liquid of the electrolyzer, as well as the temperature control that strives to keep the temperature at 70 degrees centigrade. This concludes the short demo of Apros power-to-gas electrolyzer simulation. In upcoming videos we will delve into details of gas storages and methanation. For more information about Apros and the Neocarbon Energy Research Project, please visit the web pages shown here.